Good day, folks. Welcome to Bright's Mind Academy, where we bring brilliance to every lesson. Now, let's look at question six. A very tricky topic that is very nice, but tricky, especially to most learners. Uh, KC, chemical equilibrium, right? Le Chatelier and all those stuffs. Now, okay, uh, it says to us consider the balanced equation for a hypothetical reaction that takes place in a 2 decimeter cubed sealed container. Okay, so we have that hypothetical reaction there of uh, boom, 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 boom. Okay, so now they say to us the graphs below not drawn to scale are obtained from the same reaction at two different temperatures. Okay. Graph A is obtained at a temperature of 298 Kelvin, and graph B is obtained at 398. Can you see now from here to here, there was an increase in temperature. So we'll just see how that change affected our graphs. All right. Now we have concentration versus time graph. Okay, good. Now, can we see that from the start of the reaction of the concentration of PTQ, which is our reactant, decreased again, whereas the reaction the concentration of PQT PQ2 increased from zero. Now, why is it increasing from zero? It is because initially it had nothing. Okay, so these two had to react so that it formed that. So here it is increasing. Now, can you see that from time t5 going to this side, we have reached equilibrium. Now, the rate of forward is now equal to the rate of reverse, or now the concentration are constant, or we can say now to us, uh, we can say now to us, the concentration is constant. Again, yes. So let's just dive into it. Okay, let's analyze this one. So we can see here if the concentration of P2Q decreases and this one increases, it means now in this case the forward reaction is still the one that is favored. Okay, the normal reaction occurs. Now let's look at after the change. After an increase in temperature, what happened? Can you see now this one, it is PQT. So okay, now the dotted lines now represent PQT. Now this is our product. Now can you see now after a change, after a increase in temperature, what happened? Our product decreased. Can you see now our product decreased here, whereas our reactant P2Q increased. So now it means in this case the reverse reaction was favored. Why am I saying that? Because can you check the concentration of PQ2 was decreasing. Okay, so now we see that if there was an increase in temperature, when there was an increase in temperature, what happened? The concentration of, let me just say, the reverse reaction was favored. And we know an increase in temperature favors what? Endothermic. Why are we saying an increase in temperature favors endothermic? Because now, if the temperature increases now, the system will try to do what? To absorb. So which reaction between endo and exo absorbs energy? It is the endothermic, right? So it means the forward reaction, sorry, if an increase in temperature favors the endothermic, and now the reaction that was favored was the reverse. So it tells you that the reverse reaction, it is endo, since it was the one that is favored and an increase in temperature favors endo. So it means now what does that tell us? It tells us the forward reaction, it is exo. So it means this reaction, it is changing H is less than zero. Remember, how do we check the energy of a system? We check by the forward reaction is the one that is given to us. Even if the examiner give you this is the information with regards to the forward. So it means now if the forward reaction is exo, it means now it releases heat. So it means we can add plus heat to see that it is a forward reaction. It is exo. Okay, yes. Now I want us to see something. It decreased, it decreased at time t3, it reached equilibrium. This one was increasing. Now, after, just check after at time t, just instantly at time t8, there was a sharp decrease. Can you see a sharp decrease here and a sharp decrease here before each and everyone got their momentum back. Now I will tell you the effect. If concentration was a factor here, only one was gonna spike down or drop. Okay, let's say here a concentration was decreased, so maybe this one was gonna decrease, not decrease rather, it was gonna drop a lot like that, and then this one was just gonna follow like okay, it was just gonna a little bit, then I find momentum. But in this case, both of them dropped drastically. Okay, if they increase at the same time, okay, let's say increase at the same time, and this one like that, it means now the only factor that can affect it is pressure. When the pressure of the system is decreased, or you can talk of volume, when the pressure of the system decreases, it decreases everything. Okay, so here the factor here it is pressure. Okay, the only time that you can have both of them decreasing like that or both of them spiking, it is pressure. Okay, now I'm in a position of answering. State Le Chatelier's principle. This one I leave it to you, but remember what does Le Chatelier says? It says now when the system, so when the equilibrium in a closed system, okay, closed system, not isolated system. Okay, in chemistry we use closed. In physics we use isolated. Okay, you use isolated here, you get -1. So when the equilibrium in a closed system is disturbed, what happens? The system will try to reinstate a new equilibrium by doing what? By favoring the reaction that opposes the what? The disturbance. Okay, yes. So know your definitions. What does parallel lines at T5 mean? It means now we have reached equilibrium. This one is straightforward. Equilibrium has been reached. Is the forward reaction exo or endo? Now, I already indicated that the forward reaction, it is exo. The forward reaction, it is exo. Why? Why am I saying that? Because, let me just say, first say in exo. Why? Because the first thing first that we saw, with an increase, you'll just write them in terms of good words, né? With an increase in temperature, okay? Or just say an increase in temperature favors the endothermic reaction. Okay? An increase in temperature, always, not sometimes, an increase in temperature favors endothermic reaction. But now, the reverse reaction was favored. The reverse reaction was favored. Why am I saying the reverse reaction was favored? Can you see now P2Q, which is our reactant, did what? Increased, and our product decreased. So now our reverse reaction was favored here. So now this tells us if the reverse reaction is favored and the increase in temperature favors endo. So it means now the common words is that if the if increase in temperature favors endo, and the reverse that was favored is reverse. So it means the reverse reaction is endo, then the forward reaction it is exo. Okay, yes, this is the formal explanation thereof that you need. How does the equilibrium constant Kc for the reaction in graph B compare to that in graph A? Now the Kc will decrease. Why? Because in here, remember the Kc, it is the product divided by the reactants. Now if the product increases, now Kc will increase, but now if our product decrease, Kc will also decrease. Okay, now what is happening to our product? Our product are PQ2. Can you see PQ2? It is doing what? It is decreasing. So now what will happen to that? It will cause our Kc to also do what? To decrease. Now can you see here PQ2 was increasing, so it means our Kc was increasing. So the minute you favor the reverse, every time when you favor the reverse, you do what? You decrease the Kc. Okay, so here the answer will be less than. So it means in comparison it will be less than because it was decreased. Now we are all right. As I was still continuing recording this video, basically, I already drawn the graph and all, and I was busy. I was ready to be in a position of calculating our Kc now. All right. But as I was continuing with my calculation here, I saw something that does not add up basically. Why am I saying that? Because now I want you to check this with me. P2Q rather, it is our reactant, right? Now remember, if something it is our reactant, it should start at a certain amount of concentration. Why am I saying it should start at a certain amount of concentration? Because now it is a reactant. There is no way you're going to form a product whereas you have zero reactants. So if you have zero reactants, automatically you have zero products. Okay, so here the graph here was namely wrong for P2Q. Okay, so this graph basically was supposed to be the graph of PQ2. Why? Because now PQ2 it is our reactant, sorry, our product, right? So the only time this can happen it is when our product decreasing, sorry, increasing. Our product will increase. Okay, then what will happen to our reactant? Our reactant will decrease in this case because now that's what happens, right? Yes. So now this graph is not supposed to be that, it's supposed to be P2Q. I hope you are following. Even if you were to try and calculate that, you'll see that if the initial concentration of this is zero now, there is no way you're going to get an initial amount of moles, because now how can you get an initial amount of mole if this was P2Q? Remember what we are trying to calculate, it is the initial number of moles of P2Q. If your concentration is zero, remember the formula says C it is equal to N divided by V. If your concentration is zero, automatically this should be zero, because when you multiply this by that, N is equal to zero. So that was not making sense. So I had to see what exactly the examiner was trying to do. And yeah, I understand sometimes hypothetical reactions can be confusing. So I want to believe now we are in a position of answering now. Okay. Now I want you to see that at equilibrium now, the concentration of PQ2, remember this is at equilibrium of PQ2. Let's fill up whatever that we have in terms of concentration. Okay, PQ2 PQ2 has a concentration of 0.35 at equilibrium, but initially it had what? Zero. Remember it is a product. Remember product has zero when it starts, but as it increases, can you see it has something? It started where at zero. This one will start at an unknown value. Okay, this one will start at an unknown value. Similarly, at equilibrium, you do not know its value. Okay, so for P2Q, we'll rather instead say what it is X here. Okay, now I want you to realize something. The change here, since while we are forming PQ2, this will be plus, and since while we are using P2Q, this will be minus. So how much gain did this gain? It gained 0.35 so that it can reach to this one again. But this one, on the change, we use what? Mole ratio. If we formed 0.35 moles of PQ2 and with a mole ratio of 2, how much of P2Q did we use? So it is one of this, meaning it is half of this that we use. So it means something like 0.175, if I'm not mistaken. I think 0.17 it is 0.34. Then 0.35, 175 it should be something like 0.35. Okay, I want to believe that's the correct answer, 1.75. Now, what is the change here? Can you agree with me now? The change is going to be x minus 0.17175. Okay, this is going to be the change now. Okay, sorry, the equilibrium constant. Sorry, the equilibrium concentration. Sorry, I'm just disturbed. This question ruined my mood basically. Now remember the expression says the products divided by the reactants. This has no mark. This is just reminding you what you should include reactants. You'll write the correct spelling. Your mark comes here where you say KC. It is what are your products? Your products are PQ2. Okay, your products are PQ2. And can you see now if those are my products? Okay, PQ2, never mind. Our reactant is P2Q. Okay, this is your first mark. For correctly naming your expression now, it is a mark. Okay, the examiner was even allocating 2 marks for that one. If I remember very well. Now, what is my KC? My KC, it is my equilibrium constant 0.49. 0.49. When I substitute, I use this bracket. This is 0. Oh, another thing that you should realize, this one has an exponent of 2, right? So it has a 2 here. So it means now PQ2 should have an exponent of 2. Okay, yes, I almost missed that one and it was gonna get everything incorrect. Squared, all divided by what is the concentration of this one at the equilibrium? 7 minus 0.175. Sorry, not squared. This is a mark for substituting. Okay, mark for substituting your KC, a mark for substituting everything. Then now you get, if you do a mathematical gymnastics there, you'll get that your X, which is the initial concentration, it is 0.425 mole per decimeter cubed. Now I want you to realize that this is the, let me just say X X, which is the concentration of P2Q initially, it is equal to that. Okay, so how can this help me? This can help me to get the what, the number of moles. Why am I saying X? It is initial concentration because can you see initial concentration, it is X. I wish we had a better question for better understanding, but I'll try to record some of the equilibrium so that we find the momentum of this. So now if I want the initial, remember the formula says C it is equal to N divided by V. Okay, you can manipulate the formula and say number of moles of P2Q initially. This is gonna be what? CV. What is my C? My C is my concentration, which is 0.425 multiply. What is the volume? The volume was 2. Okay, so you get something like 0.85 what? Moles. This is your final answer. This is you substituting here another mark. Then yeah, at maximum you should get 8 marks. You should using mole ratio here, it is a mark. Then doing the change here, it is a mark. Let me see how many. 1, 2, 3, 4, 5, 6, 7. Where can you get another mark? Where can you get another mark? I don't know. But yeah, 2, 4, 6, 8. No, they are correct. They are fine. Okay. Now we can move on to the last question, which says to us, best describe the change that happened in the system here. Okay, so now remember I said at time t8 the only effect should be what? Should be the pressure. Okay, but now the question is, what happened to the pressure? Did it increase? Did it decrease? The question stands, did it increase or did it decrease? Now it decreased because can you see it went down? So you're gonna say, where is it? Decrease in temperature. Sorry, not temperature. Where did I, yeah, decrease in pressure. Okay. Now what happened to a decrease in pressure? It favors the reaction that forms what? Okay, if we have a decrease in pressure, the system will try to favor the reaction that forms more number of moles. Okay, that increases number of moles. where are number of moles? Can you see now the number of moles here? It is 1 plus 3, which is 4, whereas in here we have 2. Okay, so the system will want to do what? Will want to go to that side, remember again. So now the system, if there is a decrease in temperature, sorry, in pressure, then what will happen? This will favor the reaction that leads to more, that leads to more number of moles. Or you can say that increases the number of moles again. And then now, what happened now? The concentration of P2Q did what? Increased. Okay. So for the graph, for the calculation, I had to change this. Okay. But for the reasoning and what, we also we use these as they are. Okay. I hope you are following what I'm trying to say here. So yes, I don't like this question. I should have checked it before if it had any type of error. What we try to assume is that the examiner from the department checks the mistakes, but now it seems like our department, yeah, is not necessarily caring. Because now one thing I know is that when you meet an error in an exam, it ruins your mood. Okay, so thank you very much, folks. Let's meet on question 7 under which is acid and base. Thank you.